very good afternoon to everyone. I am Shubhangi Rao and I am working as an assistant professor at MLR Institute of Technology in Department of Electrical and Electronics Engineering, and I am teaching this subject electromagnetic field to second year EEE students. And today we are going to discuss about Gauss law and its application. So let's start. So what is Gauss law? Gauss law is one of the fundamental laws of electromagnetism, and it states that a total electric flux through a closed surface will be equals to the total charge enclosed by the closed surface, right? So to understand this law better, we will consider this isotropic homogeneous medium of dielectric constant, right? So we will consider that a point charge Q is located in this homogeneous medium of dielectric constant. So if you notice here, this is the medium and here this charge is available Q, right? So we have to find out the flux density, right, which is at the distance r, right? So the flux density at a distance r on a surface which is enclosing the charge is given by vector D is equals to epsilon vector E, where E is the electric field intensity, and the formula for that is Q upon 4 pi r square AR, where AR is the unit vector. Here you can see that, right? Next, now to understand it better, we will consider one elementary area ds, right? And the amount of flux which is passing through this elementary area ds, this area is given by d xi, which is equals to vector d dot ds, and is given by Q upon 4 pi rs r square ds cos theta. But as we know that this ds cos theta upon r square is basically d ohm, which you can see here, right? It is the elementary solid angle which is subtended by area ds at the location of this Q. Therefore, this d xi can be written as Q upon 4 pi d ohms, right? And for a closed surface which is enclosing the charge, this equation therefore can be written as xi is equals to integration of s d xi is equals to Q upon 4 pi integration of s d ohm, which is equals to Q. And this is nothing but the Gauss law, right, which says, if you see in the previous slide, that the total electric flux enclosed by a closed surface will be equals to the total charge present on that surface. So this was the Gauss law. Next, we can understand its applications. So the applications of Gauss law, we can find out the electric field intensity by using Gauss law. So for that we are going to use three different arrangements. The first one is infinite line charge, right? So by using Gauss law, we are going to find out electric field intensity due to an infinite length line charge. So to understand that, we are basically considering one cylindrical surface, right? You can see here clearly this is a cylindrical surface. Basically the line charge is present on the z-axis, right? And around this z-axis we have created one cylinder, and obviously the lines of field or the electric field intensity will be like this, right? So here we are considering one closed cylindrical surface, and by using Gauss theorem we can write one application which is written as rho L is equals to Q, where rho L is the line charge density, right, and L is the length, right? So this is the infinite length line charge. So rho L is equals to Q is the charge present on that, which can be written as integration of S epsilon naught capital E ds is equals to, now if you notice here we have three different surfaces, right, three different areas. One is this S1, another one is this S3, and then this S2, this area, right? So when we elaborate this formula, it becomes integration of, for S1 surface, it becomes integration of S1 epsilon naught E dot ds plus for S2 integration of S2 epsilon naught E dot ds plus S3 epsilon naught E dot ds. Now if you notice, the unit normal vector to this area S1 and S3, they are actually perpendicular to the electric field. This is your electric field and this is perpendicular, right? So basically the surface integral for the top and bottom surfaces will be evaluated to the 0. So basically what we are left with is this, rho L is equals to epsilon naught E 2 pi r rho L, right? Basically this is the area for this cylinder. Hence this equation can be written as, because we have to find out electric field intensity, it becomes E is equals to rho L upon 2 pi epsilon naught rho a rho, where rho is the radius of the cylinder and a rho is the unit vector, rho L is the line charge density. So this was about application of Gauss law, first application of Gauss law for finding out electric field intensity due to an infinite length line charge. Next application is, we can find out electric field intensity due to infinite sheet of charge, right? So we are going to consider one sheet of charge. Here you can see we have a 3D system and there is a sheet of charge which is basically covering XZ plane, right? This is the infinite sheet of charge, so it can be elaborated in X direction, positive, negative, and Y direction, positive side and negative side. Here we have taken one differential area element, right, which is given as del S, and this is the flux density D, which is outward in both the directions, right? So by this arrangement we get the equation integration of d dot ds is equals to 2d del S, and it can be written as rho s del S, where rho s is the surface charge density, and hence after solving this particular arrangement, this equation becomes E is equals to rho s upon 2 epsilon naught ay. Ay is the unit vector, so this element is in this, on this surface, and this ay means it will be perpendicular, means in y direction. So this is the electric field intensity by using Gauss law we have found for infinite sheet of charge. Also if you notice here, this electric field intensity due to sheet of charge, it is independent of distance. Like the previous formula, here we don't have any distance. So this is free from the distance for infinite sheet of charge. But if we consider finite sheet of charge, the field will be the function of distance, right? So this is the second application of Gauss law, which was infinite sheet of, by using infinite sheet of charge you can find out electric field intensity. Next we move to another application which says, by using uniformly charged sphere we can find out electric field intensity, but by using Gauss law. So here to understand this, we have considered a radius, a sphere of a radius r0, which is having a uniform volume charge density, which is given by rv, or you can write it as rho v also, and the unit is coulomb per meter cube, and here we are finding out d. So it will be everywhere, inside and outside the sphere, and we have constructed a Gaussian surface for the radius r is greater than r0 and r less than r0. So we have these two spheres here, right? So for the first reason r, where r is less than and equals to r0, the total charge which is enclosed, it will be given by q is equals to rho v into 4 by 3 pi r cube, which is the area of sphere. So this is the first formula which we have got for r less than and equals to r0. When we apply Gauss theorem and we elaborate this formula, we simplify it, it becomes integration of d dot ds is equals to integration of, from the limit of phi will be 0 to 2 pi, and for another integration the limit of theta becomes 0 to pi, and it can be written as dr r square sine theta d theta d phi, which eventually becomes 4 pi r square dr, which is equals to q. Therefore, this d becomes r by 3 rho v AR for r less than or equals to r naught, and the range is from 0 to r naught. Now if you consider the region where r is greater than or equals to r naught, the total enclosed charge will be given by QEN is equals to rho v 4 by 3 pi r naught cube, and when you apply Gauss theorem and you use the same formula, it becomes r naught cube upon 3r square rho v AR, where AR is the unit vector, rho v is the volume charge density, r is the radius. Here the r was greater than or equals to r naught. So here we had discussed about Gauss law and its 3 applications. That is all for today. In case you have any doubts, any queries, you can write to us. Thank you very much.